Let's talk about the rate of convergence of our methods of bisection, of Newton, of the secant method, and of regular Falsi. And now we want to do the analysis, the mathematical analysis. So let's talk about this function. This function has two roots. There are two solutions. One of them is 0, and that makes the analysis much more easy, because if you have some position and this is an approximation of the root, this position is the deviation to the solution you are looking for, so analysis gets much more easy. So let's analyze the behavior if we are looking for that root, applying our algorithms. Let's start with the example root bisection. We are passing our function, which can be evaluated by the algorithm. Let's start with initial values -1 and 1, but in this case the 0, the perfect midpoint, is the solution. We don't want that to be. So let's shift a little bit left to -1 and 1, and then let's run the algorithm. What will happen? We will calculate the midpoint of these two. This is a number very close to 0. And then we exchange one of them, A and B, depending on the sign. And the midpoint is running in that way. So you see what you see every time. This midpoint for a long time, every time this is half of the one before. So speed of convergence is linear, and the factor is the length of the interval as well as the deviation of your point to the root you are looking for is halved in every step, and this is linear convergence. 2 steps means you are closer by factor 4, 3 steps means you are closer by factor 8, 4 steps means you are closer by factor 16. That is bisection. The Newton iteration is much more powerful. Starting with initial value 1, you have to pass the function, but on top you have to pass the derivative, but it's no problem in that case. Starting with 1, next point will be 0.222, 0.0167, and then deviation is 10 to the power of 4, 10 to the power of -4, it was -4, 10 to the power of -9, 10 to the power of -18, which is very close to 0, and the next step 10 to the power of -36, and it's rounded to 0. So after 1, 2, 3, 4, 5, 6 steps, the solution is found exactly. And that is fantastic. It's much faster than it was for bisection. So next is secant, and then next is regular Falsi. And after these examples, we will do the mathematical analysis. Okay, root secant, a little more steps, but in the end, we find the solution with high precision and very, very few steps compared to that. But secant needs a little more steps than Newton did, but it's in this case only, I think, two more steps, so no real problem. Regular Falsi turns out to be convergence, only linear convergence, the same as bisection was. Unfortunately, the combination of bisection and the secant method is not as good as one would expect. It's a only linear convergence. Okay, and now let's do the analysis. Let's analyze Newton. Newton is of that form, and for our specific f of x and f prime of x, okay, we can write the Newton iteration that way. So denominator is that one. Let's expand that part and bring it to the same denominator. Please do that. Then you have to multiply this times that, and then what will happen? This product and this minus, they will cancel, and what is left only is, and in that case we will get 4 times xn squared minus 2 times xn squared, and we end with that. And we can rearrange that, write that at the end after the fraction, and you can write it that. And what does that mean? What do we see? We see if xn is close to 0, this will be approximately 2 divided by 5, 0.4. 0.4 times the last xn squared. The last xn squared, and this is the quadratic convergence, and there is a factor on top, which is 2 divided by 5. What does quadratic convergence mean? That means if you are close in one step, or so let's say in step number 4, step number 5, you will be much closer, and step number 6, you will be much closer. If x is 0.1 here, if this is true, then you will have the square of 0.1, which is 0.01. This is a point. In Germany we use the comma instead of the decimal point. It should be a decimal point. If you square that, you will get a lot more zeros. So 10 to the power of minus 2 squared is 10 to the power of minus 4. And so minus 1, minus 2, minus 3, minus 4. This number squared is that. And one more step means you have a lot of more correct digits. And if you do one more step, you have 15 correct digits. That means quadratic convergence. It means if you are close, you will be much closer than linear convergence will do. If you want to do the step from here to here with linear convergence, it would need a lot of iterations. Okay, and in our example we see that sequence, and you see 10 to the power of minus 2 to the power of minus 4 to the power of minus 9. The factor 2 divided by 5 helps on top, 10 to the power of minus 18. Fantastic speed of convergence. And for this function we analyzed in detail why convergence is quadratic, and later I will tell you that our example function is not a specific one. It will be more or less always of that kind. Okay, so we understood Newton's method, and the next one we want to analyze is the secant method. The secant method is that recursion. Having xn and xn minus 1, you get the new xn plus 1 by applying that. And what can we do in this situation? We know what is f of x, so let's write that here. What is f of xn? It's that. And what is that here? And so on. And now, what can we do? We can rearrange that in that form. Okay. And we can rearrange that in that form. Check every single detail. It's not a hard task, but yes, you can rewrite this one in that form, and this one is more simple. Then you can further do something. You see that, and you know binomial formula a plus b times a minus b is equal to a squared minus b squared. You can use the formula from top down, and we do the opposite. We use it from here to here. So you can write that in that form. And if we did so, we find it here, we find that here, we find that here, and so you can cancel that and you get this one. We can write that here, and then you have 2, only a 2, and here we have 5, only a 5, and here we have 2 times that, and that's what we have here. So what do we see? We see if we are close to 0, then xn and xn minus 1 is not much more than 0. So this product is close to 0, so this is close to 5, so this is close to 2 divided by 5, so we have 2 divided by 5 times that. Okay, so that's an interesting recurrence. What does that tell us? Do we have quadratic convergence or linear or whatever? So we can analyze this in the following way. First we can check the example, but we already did. And next we can make the Ansatz. Ansatz is a German word, and English sometimes takes German words. Kindergarten is also an example of that. And Ansatz is another one. In mathematics or in science, you can say we make the Ansatz, we make the approach, and we assume you can write xn plus 1 as a power of the last xn, and we are looking for the k. We don't know the k, but we assume there is a k, and then we can write it that way. So let's analyze this. So if this is true, so 2 steps means xn is xn minus 1 to the power of k. This is xn, and then to the power of k. Then you can multiply these two and you get this squared. So xn plus 1 is this one. Okay, so here I wrote it for that part again, and then on this side we can write xn to be xn minus 1 to the power of k. So knowing that this is true, we can rewrite xn by that, and we get this line. What do we have? Xn minus 1, xn minus 1, xn minus 1. All three are xn minus 1, and not as it was an xn and xn plus 1, but all three are xn minus 1. So multiplying something to the power of k times something to the power of 1 is something to the power of add the exponent, so k plus 1. Divide the equation by that, and then you get k squared minus k minus 1 on the left hand side and 1 on the right hand side. Some number to the power of something is 1 if and only if this is a 0. So we come to that equation, and now we can apply ABC formula to get this one, and this one is square root 5. And square root 5 plus 1 divided by 2 is 1.6180. K is this one, and thus this is the assumption. Xn is xn minus 1 to the power of 1.618. And this is, by the way, the golden mean number. Okay, the convergence speed is of order 1.61. And if you apply 2 steps, you are of order more than 2, so it's not quadratic convergent, but close to quadratic convergent, and that means if Newton is fast, the secant is a little less fast, but not significantly less fast. And that means we have some form of multiplicative Fibonacci sequence. What is Fibonacci? You start with the numbers 0 and 1, and then the sum of these is 1. The sum of the last 2 ones is 2. The sum of the last 2 is 3. The sum of these, the last 2 ones, are 5, 8, 13, 21, 34, 55, 89, 144, and we can continue and continue as long as we want. This is the Fibonacci sequence, and that is the convergence is of the form a multiplicative Fibonacci sequence. Very, very interesting. Fibonacci numbers show up from time to time in mathematics in situations, and you absolutely did not expect them to show up. That's the truth for being a mathematician. Yeah, not every day they show up, but from time to time, and always you are very astonished. Regular Falsi is convergent only, we have only linear convergence, and now we do the analysis. This is the recursion of regular Falsi, and then you can write it that way. And you always will replace the same side when applying regular Falsi for our example, because of the convex nature of the function. Convex means second derivative is positive, and that means if you start with that point to be A, that point to be B, then you take the secant, take the root of the secant, then you evaluate the function at this root, and then you check the sign of the function value, and because this one is negative, you will replace A, and that will keep being true over and over again. And so we know that we have this situation, and then we get an plus 1 is more or less 2 divided by 7 times a1, and that means we have linear convergence. If an is close to 0, this is close to 0, and what is left is minus 2 divided by minus 7, which is more or less 2 divided by 7. So convergence is only linear, and we did the analysis to see that in detail. And if you check this sequence, you can see the factor 2 divided by 7. Take this number, multiply it by 2 divided by 7, and you will end close to that number. Multiply this number by 2 divided by 7, and you get more or less this number. You see exactly the number 2 divided by 7, so our analysis is of great value. And applying the sequence and checking value to value, what will happen, you see always what our analysis told us. So our example, maybe you say, okay, what is that example? 5 times x plus 2 times x squared. What is that function? It is some function where the first derivative at the root is non-zero or positive number, and the second derivative as well is non-zero. And this is the situation, the normal situation, the situation where convergence, speed of convergence is like our analysis told us in advance. And if one of the derivatives is 0, then everything changes. But as long as the derivative, the first and the second derivative at the root is non-zero, this analysis holds true, because you can develop every function, analytic function, in a Taylor series, and then you have a first and a second derivative, and that means there was nothing special. If you're a mathematician and you further want to be more general, then you say, okay, we have a function and this is some number c1, and the second derivative gives us the factor before the x squared, and then you can find out that Newton's method converges quadratically, and the factor before is the c2 divided by c1. For the secant method, it's again c2 divided by c1 times the power of 1.618. And regular Falsi is of linear convergence, and the type is b divided by c1 plus c2, where b is the starting point with the positive function value. If the derivative at the 0 you are looking for is 0, then everything changes and our analysis is no longer true. You will lose the superlinear for all the methods, for Newton, for secant, and you will be only linear convergent, and the bisection in that case is more or less the best you can do. So this is our analysis, and if you want to check all that, if it fits to our analysis here, I told you why it is completely correct. And the function I mentioned here, we also already saw this was the rope around the world in the tangent version. So this was our analysis, and being a mathematician, this was a great pleasure. If you see that for the first time, it's the opposite of great pleasure, but if you try to understand and in the end you understand, you will see that this is of very high quality. We have an exact analysis. This is brilliant mathematics and I enjoy that, but you need a lot of time to get familiar with all the details. In the end, if you understood all the details, then you also understood the great picture, then it's of great value what we did, and it's a great pleasure to be able to understand all that in detail.